Okay, problem 1 on the study guide. Find inverse function f of x if the regular function f of x equals 5x plus 1, stating the restrictions on the domain of f inverse of x. So we first of all start off with f of x, which is 5x plus 1, and consider its domain and range. We can see that we're multiplying x times 5, we're adding 1, there's no any restrictions whatsoever on a multiplication or addition function. So the domain is a set of all real numbers. And as far as the range is concerned, if I was to graph this, it has a slope of 5 and a y-intercept of 1. So, you know, if you have a y-intercept of 1 and a slope of 5, it's going to do something like that. So it's going to be just some line that goes as far up and as far down as you can assume. So we can see the domain, or should say the range of that, is also the set of all real numbers. Once we've established this information about our original function, now we go on to make the inverse function. Keep in mind f of x basically is about what y is, so y equals 5x plus 1. To make an inverse function, we swap the x and the y variables, so x becomes y and y becomes x, so x equals 5y plus 1. And just like that, I made the inverse function. What's left to do is to make an f inverse of x like this. We want this to say y equals down here. So if I move the 1 over, I get x minus 1 equals 5y. Divide both sides by 5. We get y equals x minus 1 over 5. So my inverse function is going to be x minus 1 all over 5. As far as the domain is concerned, the domain of the inverse function matches the range of the original function. So the domain of this is all real numbers. And that'd be the final answer for that one. Number 2, same problem, same type of problem. This time we're going to deal with a radical function. Imagine that we have the square root of x minus 5. So 5 comma 0 is a point. And then if we get x bigger, because x is bigger than 5, larger than or equal to 5 is what that says. So if x is 6, 6 minus 1 is 1, the square root of 1 is 1. And if I did 9 minus 5 is 4, the square root of 4 is 2. Just if you can imagine what the graph looks like, it's increasing in size forever. So as x continues to get bigger, y is going to continue to get bigger all the way to infinity. So as far as domain and range of the original function are concerned, the domain is what they gave to me. Domain is a set of all x such that x is greater than or equal to 5. The range is the set of all y, not y, f of x. Set of all f of x such that f of x is greater than or equal to 0. Again, this is for f of x equals the square root of x minus 5. So once we've established, again, the domain and range of our original function, now we go on to make the inverse function. So if I take the original function here, change f of x to y, and y is just an easier notation when we're doing inverse functions. So I'll make the f of x become a y. To make an inverse function, x becomes y, y becomes x. And then what's left to do is to solve for y. I've got a square root in the problem, so I'm going to square root both sides. So the left side becomes x squared, the right side becomes y minus 5 without the radical. Move the 5 to the other side, we get x squared plus 5 is equal to y. So this is the inverse function here. So again, I'm going to write a good inverse notation. So f inverse of x equals x squared plus 5. And if you notice, the inverse function here is a polynomial function. We can square anything, we can add 5 to anything. So if I was just looking at this all by itself without considering anything else, I'd say all real numbers. But the domain of my inverse function has to match the range of my original function. So the domain of this is the set of all x's such that x is greater than or equal to 0. Okay, even though this says f of x, we swapped x and y. So f of x, the original function, is x of our inverse function. So use the exact same range, just change f of x and f of x into x's to identify it as a domain. So for this problem here specifically, we're only allowed to pick numbers greater than or equal to 0 if I wanted to actually graph the inverse function to the original function. Okay, number 3, evaluate g of x equals 1/2 of the x power for x equals 4, x equals -2. So g of 4 equals, and the function g of x is 1/2 to the x, so it's going to be 1/2 to the 4th. All you have to do to take any fraction to a power is to take the top number to the power. 1 to the 4th power is 1. Take the bottom to the power. 2 to the 4th is 16. So 1/16 is the answer. If I want to do g of -2, that's going to be 1/2 to the -2nd power. If you're doing a fraction to a negative power, that's the same as taking its reciprocal to the positive power. So instead of 1/2 to the -2nd, I'd rather go 2 to the positive second. And that's just going to be 4 over 1. So g of -2 is equal to 4. On the test, I would expect one of those, not both, but I would expect a fraction or a whole number answer. Don't give me decimals for that problem. Number 4, sketch the graph f of x equals 2 to the x power. What I told you in class about an exponential function, the 3 powers I want are the negative first, the 0, and the first power, because we can do those without a calculator. It's real simple. -1 reciprocates. The reciprocal of 2 is 1/2. 1/2 is equal to 0.5. Anything with the 0 power is equal to 1. Anything with the first power equals itself. If I did a second power, 2 squared is equal to 4. If I did a third power, 2 to the third power is equal to 8. Again, no calculator necessary. If it is necessary, of course, y1 equals 2 to the x power, and then just type a bunch of numbers in your table there to get some values. I do want to see the table filled out on your paper to see where your number is coming from. Looking at this graph, I've got enough room to go up 8 spaces, so I'm going to go to 1-to-1 scale. You don't have to mark a 1-to-1 scale, but if you do scale ever, just make sure that both scales are identified. -1, 0.5. We got 0, 1, 1, 2, 2, 4, 3, 8. 4 would be 16. That's off the scale. I could come back this way a little bit if I wanted to. Decimal approximations, find 0.25, 0.125. And with our knowledge of exponential functions, this is that bend we're going to get with our 3 numbers we're supposed to pick. One side goes up, one side flattens out. The side that flattens out is going to usually flatten out to 0. Imagine if we pick some big power here, 2 to the -500th power, for example. That's 1 over 2 to the 500th power. That's a positive number. 1 over, in very, very large, goes to 0, but not quite. So we're going to have a horizontal asymptote here at y equals 0. So if I just go ahead and connect the dots with a nice smooth curve, there's my exponential function. Make sure you don't cross the x-axis, because again, if we pick some huge number, we're getting almost 0 but not 0. It never becomes negative, never becomes 0. So officially there is a horizontal asymptote that you should draw in also, right there at y equals 0. So I would expect to see the graph along with the horizontal asymptote drawn. If you write HA of y equals 0 also, that wouldn't hurt as far as showing work is concerned. But just know that the reason why is as x increasingly gets smaller, you're getting a bigger and bigger and bigger number underneath 1, so it's getting closer and closer and closer to 0. Number 5, the function a of t is equal to 300 e to the -0.007 t gives the amount of medication in milligrams in a patient's bloodstream t minutes after the medication has been injected into the patient's bloodstream. Find the amount of medication in the nearest milligram in the patient's bloodstream after 35 minutes. Use a graphing utility to determine how long it will take the nearest minute for the amount of medication in the patient's bloodstream to reach 100 minute 80 milligrams. So this is right in this 4.2 section we were dealing with. We have a function, and they tell us specifically what things in the function represent. So a of t is the amount of medication in milligrams, and t is the number of minutes after the medication has been injected. So we have to understand when we look at an equation what things in the equation represent. E is the number E, that's the magic number 2.718 and so on that we've been investigating here recently. So for part A, find the amount of medication. They want us to find A when t is 35. So basically part A is simply asking us what does A of 35 equal. And to do that, it's real simple. We go to our calculator, we enter the function, go y equals, clear out whatever's in there, type in 300 e, always get e by second ln, that brings up e caret parentheses, negative 0.007 x. Okay, for the sake of my calculator, x is representing the time, y is representing the amount of medication. Go over to my table, delete out stuff that's in there. Again, my concern is at 35 minutes, and it's 234.81. The question says to the nearest milligram, so that's what it comes out to on my calculator, so what I'm going to put is 235 milligrams. I'm fine with this number being on your paper, just make sure you've rounded it correctly on your answer that you circle. Use a graphing utility to determine how long it will take to the nearest minute for the amount of medication in the patient's bloodstream to reach 180 milligrams. So, if I just look at this problem, and again, if I just look at my stuff here, at 0 minutes, I can see that we're at 300. After 35 minutes, we're down to 235, so it's decreasing through time. All right? We're going to get 180, so obviously the answer happens after 35. Now, my goal is to find out when it equals exactly 180, so I'm going to type in 180 for this. And then I'm going to set a window. And my window, I'm going to go from 35, because I know it's only at 35 minutes. We can see it's at 235, not 180 yet. I don't know how long it's going to take, so I'm going to go up to 100 minutes. It might take that long, it might take less, who knows. And I'm going to go 10 minutes at a time. So every dash represents 10. It won't have a dash of 35. 40 would be the first dash, then 50, 60, and so on. As far as y minimax are concerned, I'm concerned about 180. So if I go from 0 to 300, 180 is in that window. Hit graph, and I should see there's my medication curve, the blue curve. And there's my 180 curve, or line, the straight line there. So my goal is to figure out where time-wise that happens. So 40, 50, 60, 70, between 70 and 80 I can tell. All right, so if I go calc, intersect, and I've only got two graphs and they only intersect in one spot. So first curve, enter, second curve, enter, guess, enter. And it tells me 72.975 minutes. It says to the nearest minute. So again, it takes, t is that many minutes. Again, it's fine to write that on your paper, but then round to the nearest minute, so we're looking at 73 minutes is the correct answer to part B there. So make sure that you're rounding correctly in that problem. And again, it's going to be set up similarly to that. If this had said like 140 milligrams and we're trying to get 180, then I know the answer between 0 and 35 at that point, so my window would go from 0 to 35 on the x-axis instead of 35 on up. Number 6, number of bass in lakes given by this function. T is the number of months that have passed since the lake was stocked with bass. So again, focusing on the equation they give me, P of T is the number of bass in the lake, and T is the number of months that have passed since the lake was stocked with bass. Okay, make sure they give you an equation that you know what the variables in the equation represent. E is still the same E that we've been using. So, how many bass were in the lake immediately after it was stocked? That means T is equal to 0 months. We want to find P of 0. So what I want you to do on these problems is to translate what the words mean in relation to the function they give us. In this case, immediately after it's stocked, we're looking for P of 0. How many bass were in the lake 1 year after it was stocked? Now, T is the number of months, not the number of years. So if they say 1 year after it was stocked, that'd be 12 months. And we're looking for a number of bass again, so P of 12 is what we're concerned with. And then finally, question C, what will happen to the bass population as T increases without bound? In other words, T gets really big. What happens to P? All right? Usually when I ask a question like that, that represents a horizontal asymptote. So just let T get really big. You might consider a graph first, see where the graph goes horizontal. So if I first of all graph, I should say type in this equation, we've got 4,500 on top, divided by parentheses, 1 plus 8e to the negative 0.06 x. end parentheses for the power, end parentheses for the division. I go to my table, and the first thing I care about is P of 0, P of 12. That's just a matter of putting 0 and 12 in my table. And we can see there are 500 bass initially, and there's 919.49, 4898. So let's go 919 bass after 12 months, or 1 year. All right, round to the nearest whole number when you're dealing with animals. Now the question C, what will happen as the population increases without bound? Now this is a situation where maybe graphing would be helpful. So I'm going to set my window from 0 to 100, and maybe from 0 to 1500. I don't know, it seems like it's growing pretty rapidly, so that might be enough. If my graph fits on the screen, that's perfect. If not, I'm going to have to make it bigger. Take a look at the graph, and yeah, it goes off the screen. So we didn't go high enough. Maybe it didn't go far enough either, but I can't tell until I see more of the graph. Again, I'm looking for a horizontal line. So if I bump this up to 3,000, climbing, 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 and it still gets off. But you can see it's kind of going upward, and then it starts to curve back the other way a little bit there. So I can see that it looks like it might be going horizontal, but I still can't tell. Let's go up to 6,000. There's no magic way to do this at this point for you guys, so just kind of making the scale a little bigger so don't get too many dashes over here. Still got quite a few. There it is going up, and there it is starting to flatten out. Still kind of climbing a little bit there, so I can't be sure of that yet. So now it looks like I've gotten high enough. Let me just go a little further out. Let's go up to 500 instead of 100. And there it is going up pretty rapidly, and there it is flattening out. So looks like the flattening out happens as we go up to 500. That should be good enough. Go to my table. 500 months later, 4,500 bass. So part C, 4,500 bass. All right. Just to verify that 4,500, as t gets extremely large, that becomes a negative power, 8 over some big number. This term here goes to 0 eventually, leaving us with 4,500 over 1, which is what we got. So that verifies what we expected based on our graph. Number 7, change m to the y power equals h to logarithmic form. And to change the logarithmic form, it's always log of the power, or I should say of the answer, base the base equals the power. So it's just a matter of rearranging it just like we did in class. That's how you write a logarithmic expression from an exponential. So log of whatever this thing is, base whatever that thing is, equals the power every single time. Number 8, evaluate log of 1/128 base 2 without a calculator. There is no log base 2 button on your calculator, so obviously we can't do it with a calculator at this point. What I want to do is consider that 1/128 is equal to 2 to some power. If I can get this to be 2 to some power, the bases are the same. So whatever this thing is here is what goes here. So if I consider 128, if we do 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. 1, 2, 3, 4, 5, 6, 7. It will work out that way on the test. So whatever this number is here, just keep multiplying by itself until you get the number in the fraction. In this case, since it is a fraction, it's actually 2 to the negative 7th equals 2 to the x. So the x power here is 2 to the 7th. So that's the power we're looking for. So 1/128 is the same as 2 to the negative 7th power. We're doing log base 2. And once we get the base of the logarithm to match the base of the argument, the answer is the exponent. So negative 7 is the answer to that problem. So again, expect the problem on the test to work out the same way. that whatever this is can be written as this number to a power, and then once you get it written to that number to a power, these match, so that's the answer. Number 9, find the domain of this. Logarithms have a restriction on them of this thing has to be greater than 0. So if you do log of anything, the anything has to be greater than 0. Not greater than or equal to, but actually greater than 0. So this gets me to x is greater than 4. That's all there is to that. Number 9 on the quiz will be a logarithm. You simply have to set the argument, whatever you're taking the log of, greater than 0, solve that. Number 10, the following function models the average typing speed S in words per minute of a student has been typing for T months. Again, they give us a function, they tell us what things in the function represent. S of T is the typing speed in words per minute. T is the number of months. And T has a restriction on it of only between 0 and 20. So we can't get an answer outside of that region for T if we have to figure out anything about T. Okay, again, my calculator doesn't know about S's and T's, so it knows about Y's and X's. So what I would do first is I would take my calculator, delete all the stuff we've got in there already, go to Y equals, clear that out, and then type in my function. So I got 10 plus 31 ln parentheses and x plus 1 n parentheses. So I type in exactly what I've got there. And part A says, what was the student's average typing speed to the nearest word per minute when the student first started to type? What was the student's average typing speed to the nearest word per minute after 7 months? So this is 2 questions. For this question, first started to type would be T equals 0, so we're looking for what does S of 0 equal. For this question, what was the student's average typing speed to the nearest word per minute after 7 months? So T equals 7 months, we're trying to find S, so S of 7 equals. So those are pretty simple to answer. They do say to the nearest word per minute, so make sure you're rounding them to the nearest word per minute. Part B, use a graph of S to determine how long to the nearest tenth of a month it will take the student to achieve an average typing speed of 85 words per minute. So this part C, they want us to have S of T equal 85 words per minute. Their question is, what is T? So we're going to use a graph to do that, very similar to how we did on the BAS problem. So, I should say not the BAS problem, but the medication problem. So I got my equation typed in. Part A is to figure out what S of 0 equals, what S of 7 equals. So S of 0 is 10. And S of 7 is 74.463. Okay, they did ask for the nearest word per minute, so for this part I would say 10 words per minute. That's WPM. And for the other part of the question, we go with 74 WPM. So for part A, those are the answers to that. For part B, we want the average typing speed to be 85 words per minute. We can see that the students increase in their typing speed with this logarithmic function. Started off at 10, got up to 74 in 7 months. He's only going to be typing for 20 months, so if I'm setting stuff up here, going to my window, we're letting x represent t in our function, so we're only going from 0 to 20 because that's all this function is alive for. I'm going to go a scale of 2. As far as y is concerned, let's start him off at 0 words per minute. We want him to type 85 words per minute, so I want to be able to see 85, so let's go up to 100. It doesn't matter if we get to see the top of the graph. So right here, this is his typing graph. That's his words per minute. He actually gets above 100 before the 20 months is up. That's pretty good. All right, but what I care about is 85. 10, 20, 30, 40, 50, 60, 70, 85 would be about here, somewhere in there. So if I go y equals, and I make y2 equal 85, that's the actual number of words per minute we want. The red line represents the 85 word per minute threshold, and you can see that it happens somewhere around here. And to find the actual intersection point, we go second calc. Number 5 is intersect. We've only got 2 curves and 1 point of intersection, so enter, enter, enter. We get 10.2386 something. T equals 10.2386. It does say to the nearest tenth of a month. So round to the nearest tenth, we're going to get 10.3 months, or sorry, 10.2 months. Okay, you should expect the problem on the quiz to be very much like that one, so hopefully you're comfortable with how to enter this stuff in your calculator. And again, making complete and total sense of what the variables in the equation mean and what these questions specifically are asking about those variables to know how to apply that using your calculator to get the correct answers.